In this video, I'm going to show you how to use the program for nonlinear regression. We'll go down to the button where the program is. It's right here. When I click on it, a set of instructions appears in the description box. I'm not going to go over these instructions with you because I'll be showing you how to use the program here. Down here is the input values box where we input information into the program. The analysis uses raw data, so we're going to go get the data file. I'm going to click on Choose File. Goes to the folder where the data is located, and we're going to be using the data ebbingr.txt. Up here, I type in the full folder name where the data are located, and I repeat the name of the data file. This is so that the program can find the data on your computer for purposes of data analysis. Okay, let me describe the example we're going to use to illustrate the program. Suppose I have people read material to increase their knowledge about a new product, such as a vaccine. I measure their knowledge on a knowledge test that ranges from 0 to 100, with higher scores indicating more knowledge. The knowledge they gain from the material usually will decay over time due to forgetting. I measure their knowledge at different points in time to see how much the average level of knowledge changes with time. I measure knowledge for some people right after they've been exposed to the material. Others I wait 1 month to assess their knowledge. Others 2 months, others 3 months, and so on through 9 months post-exposure. I do not use a repeated measure design because if I keep administering the same knowledge test to people, that in and of itself can influence their performance on later knowledge tests. Now, one way I can model the relationship between knowledge retention and time passed is to use linear regression per the following equation. Here I'm regressing a person's knowledge score onto the number of months that passed before the knowledge was assessed. Let's suppose I analyze the data and I obtain these results right here. From this equation, I can state that when the number of months passed is 0, the mean knowledge score is estimated to be 37, which is the value of the intercept. This is because in a linear regression, the intercept is the mean outcome when all predictors equal 0. When the number of months passed equals 1, the mean knowledge score reduces by 4 based on the slope here and is predicted to be 33. When the number of months passed equals 2, the mean knowledge score is predicted to go down by 4 more units and it would equal 29. The problem with this analytic strategy is that it assumes the decay curve for knowledge as a function of time is linear. There's considerable research on memory dynamics to suggest that this will not be the case. Suppose I decide to explore the shape of the decay curve empirically by examining the smoother for the data. To do so, I use the program on my website called Bivariate Smoother. Here is the plot that results from the current data. Now, the smoother is a scatter plot that plots the data, but we're used to seeing one with a straight line on it, namely the regression line. This program plots a curved line to reflect the curvature in the data, and that line is called a smooth. You can see that the curve is clearly nonlinear, and it seems to be captured by a single bend down here. Given this, a second strategy I might use to analyze the data is to apply polynomial regression with a quadratic term to capture the bend, like this. Here I have the knowledge score, here's months, and here's months squared to reflect the quadratic equation. If I analyze the data, I come up with the following equation. To evaluate model fit, I can plot the mean knowledge scores as a function of months passed that I obtained in the data and compare this to the predicted mean knowledge at each month based on the quadratic equation. Here's the plot I get. Okay, now in this plot, the observed data or the actual means connected by lines are the black line and the dashed line are the predicted means. The correspondence between the predicted means and the actual means looks reasonable. However, there's one bothersome feature of the plot. Notice that the curve for the predicted means goes down, flattens, and then starts to bend back upwards. This is a characteristic of quadratic polynomials, and it makes no sense in this case. This bend upward violates what we know typically happens. Researchers sometimes don't realize that polynomial regression implies a specific type of nonlinearity, and sometimes that particular type of nonlinearity does not hold. This is the case here. So I decided to try a different type of nonlinear modeling using classic nonlinear regression without polynomials. This type of modeling is more advanced, and you have to be skilled at mathematical modeling to pull it off. In another book I've written on theory construction, published by Guilford Press, I have a chapter that teaches you the ins and outs of mathematical modeling. So I recommend you consult that book to learn more about the process of constructing nonlinear math models. Now, a widely studied function of forgetting that has been isolated in research on memory is based on the work of Ebbinghaus. It's represented by the following equation, this one here. In this equation, A and B are unknown constants that are to be estimated from the data, much like we estimate a slope and an intercept when we conduct a linear regression. The E is the Neperian constant associated with a natural log. It equals the constant 2.718281828459, and then a few more decimals. So I can rewrite the equation substituting in the value of E here. Another way of writing this is using exponent notation as follows, right here, where exp means take the exponent of. Now the Ebbinghaus formulation takes advantage of an interesting mathematical property about logs and exponents. It turns out that the exponent of the number 0 will always equal 1. For the group of people for whom I assess immediate recall at month 0, the equation looks like this. First I have the Ebbinghaus formulation. I express it using an exponent. Because the months passed is 0, this term up here becomes 0. So I have a times the exponent of 0, and that's a times 1, which is equal to just a. So parameter A in the equation reflects the mean knowledge score for people in the immediate recall condition, or when time, in this case months, equals 0. In other words, A has meaningful interpretation, and we will be interested in the value of it. Now, to better see the implications of the Ebbinghaus model, I'm going to plot different curves for it using the multiple curve programs on my website. Right now we have an intuitive feel for what the parameter A means, but what about B? Let's take a look. So I'm going to go back up here to the programs, to the multiple curve plot, which is right here. I'm going to click on that. And the instructions for it appear here. And I'm going to go to the input values box for multiple curves. I'm going to type in the right side of the function here. But I've got to modify it. First, the program assumes the name of the predictor variable of interest is X, capital X. So I'm going to change minus months to X. Now we're not going to be using data from the data file itself. The program's going to generate simulated data for X in order to show us what the curve looks like. So I can go ahead and use the notation X there. I have to provide values for the constants A and B. So I'm going to change A to 60, which means I think that the mean knowledge score for people in the immediate recall condition will be about 60. And then I'm going to alter the value of B across 4 different instances of the function so that we can then see what the value of B is doing when the program plots these curves. So I'm going to change B to the value of 3 here. And then I'm going to copy this and paste it in these other functions. And I'm going to change b to 2 here. I'm going to change b to 1 here. And I'm going to change b to 0.5 here. Now I picked out 3 because I know the Ebbinghaus curve. And I know this is going to produce a reasonable curve. Usually when you work with nonlinear functions, you have to have a little bit of knowledge of them, but you can explore around and try any number you want to on this. Okay, so the program's going to plot 4 curves for me on the same graph, and I'm going to see what happens to these curves as I vary the b parameter. Okay, I also have to indicate the low and high scores on x. That'll be 0 to 9. I have to give a label for the x-axis. That'll be months. And a label for the y-axis, which will be knowledge. This parameter here will plot the lines either with different colors or using solid lines or dashed lines. If you want solid lines or dashed lines, you enter the number 2. And that's explained in the instructions up here. If you want different colors, you use the number 1. So I'm going to go ahead and leave 1 in this case. I hit register input to generate the R syntax for the program. I copy that to the clipboard. I open up R. Up here, I'm going to hit Control V to paste the syntax, and as it pastes, it'll execute. Okay, here's the plot that the program generated. Here are the different equations we used in the color code for those. And you can see that when b equals 3, the black line, the decay in the memory for the information is somewhat modest. Whereas when b equals 2, the decay initially is much more severe. And as b gets lower, the decay drops off much faster. Okay, so the question's going to be, which of these curves best describes what's happening in the data? What is the value of b? Is it going to be 3? Is it going to be 2? Is it going to be 1? Is it going to be 0.5? Or some number in between those? We have to analyze the data and apply the nonlinear regression program to find out. Okay, I'm going to close this. And we'll go back to the nonlinear regression program. And I'll come down to the input values box. And now I have to enter in the information here in order to do the analysis. Okay, I'm going to begin by putting the Ebbinghaus equation here. So let me type it in and then I'll explain it to you. So on the extreme left is the outcome variable, which is the knowledge score from the database over here. And then in place of an equal sign, there's a little squiggly line, a tilde, that is part of the format that R uses for expressing regression equations. Here's my constant A and the exponent of my variable months. And then there's the constant B. Now for each of the constants up in this box, you have to give the program a starting value. This is your best guess about what you think the 2 constants that it has to estimate will take on. So I'm going to use as a starting value A is equal to 60, and I'll use B is equal to 1 up here. Now if you're not sure about what a starting value is, a safe practice is usually just to give the value 1, and the program will usually do just fine with that as a starting value. The algorithm for estimation is pretty sophisticated, so in some ways the starting values don't matter that much. But I'll go ahead and put 60 because I think that's a reasonable guess of what the knowledge score will be in the immediate recall condition. And then we have the value 1 here. Now I'll explain these profile boxes to you later. We don't need them for this run. You can ask the program for a smoothed plot of the mean outcome variable as a function of a variable in the model called a generic x, and the predicted y means from the model as a function of x. In the current case, x is months because it's the only variable in the model. So I'm going to get a smooth plot, and I'm going to put the variable months in here. And that's telling the program I'd like to see the smooth plot to help me evaluate fit. If your model has more than one predictor variable in it, you can only choose one. To skip the plot, leave the box target X to plot blank and ignore the bins box. By putting a name in the box, I'm telling the program I want to see the plot. When you enter the name of the variable, make sure it is case sensitive and maps on exactly to the way it's phrased over here in the data file. And I put an extra S on it, so I got to get rid of that. Now, if the chosen X variable has a very large number of values, you may want to bin it into groups. If not, just leave the number of bins box as 0. Otherwise, change the 0 to the number of bins that you want. If the number of bins is greater than 1, the program will categorize the target X variable into bins based on quantiles. For example, 2 bins uses a median split, 3 bins uses the quantiles 0.33 and 0.67 as breakpoints. 4 bins uses quantiles 0.25, 0.50, and 0.75 as breakpoints, and so on. An entry other than 0 should only be present for a many-valued quantitative variable. Do not use qualitative variables here. You usually will not have more than 10 bins, but you can. And you want each bin to have an adequate n in it so that its mean is reasonably stable. And this requires that you not make too many bins. The assigned bin numbers are integer and range from a low of 1 to a high of the number of bins. Bins are only used for plots. They're not used in the formal algorithms. Finally, you must provide a comma delimited list of all variables in the model, including the outcome. So I have the variable no, and I have the variable month. Again, make sure you make the list case sensitive. In some cases, your entry may extend beyond the visible box, and that is okay. For example, if I had other variables like age, education, see how it extends beyond the box. That doesn't matter. The program will pick it up anyway. Basically, the entire box is going to be read by the computer. Okay, with that, I've input all the relevant information. So I'm going to hit register input. That'll generate the syntax to paste into R. I copy that to the clipboard. I open R. Over here, I hit Control V to paste the syntax. And as it pastes, it'll execute. Okay, the output is in blue and the syntax is in red. So we come up to the start of the output in blue. I'll talk through this output first, and then we'll take a look at the plots that are generated. So this is the sample size. This is the correlation between the predicted and observed values. It's analogous to a multiple correlation, and it was 0.68, which is pretty reasonable. Some nonlinear programs report R squared, but that's controversial, and it's better just to report the correlation itself. Here the program reports a model AIC and BIC if you want to use those to compare models. But that's beyond the scope of our application here, so I'm not going to go into that. Here are the parameter estimates of the model. And in this case, A is estimated to be 55.5 and B is estimated to be 2.58. You get a standard error for each parameter. And if you double those, that'll give you a sense of the margin of error associated with these guys. A t-value testing the statistical significance of the parameter values. and a p-value. The residual standard error can be interpreted roughly as the average discrepancy between the predicted and the observed knowledge scores. In this case, the predicted scores were off on average by about 15 units. That's a fairly sizable chunk. Down here are the confidence intervals for the two constants that we estimated. And then I report bootstrap estimates of the constants that we estimated. This is a sensitivity test because the prior analysis, as we'll see in a minute, makes assumptions about normality and variance homogeneity. Bootstrapping doesn't. I discuss bootstrapping in my book, so if you're unfamiliar with it, take a look in my book to learn about it. Over here are the estimates for the two constants, and these are the same as in the regression equation. Here's the bootstrapped estimated standard error. Over here are the medians of the two constants in the bootstrap distribution. Down here are the bootstrap confidence intervals. These are percentile confidence intervals. And notice that these are wider than in the original model. There's the original confidence intervals here. I trust the bootstrap estimates a little bit more because, as you'll see in a minute, there is some non-normality in the data and some variance heterogeneity. And these estimates are sensitive to that. These estimates are not. Okay, let's take a closer look at the plots that the program generated. There are actually several plots, and they're stacked on top of each other. And I'm going to move this one over. But let's consider the other plots first. A nonlinear regression, like linear regression, makes assumptions. The major assumptions it makes are that the disturbance term is normally distributed. That's normality. That the disturbance variances are homogeneous, that's homoskedasticity, and that the disturbance terms are independent. Now this plot here addresses if the disturbance scores are normally distributed. It provides a density plot of the disturbance scores with a normal distribution imposed on them. If the disturbances are normally distributed, there should be close correspondence between these two curves. The normal curve is in blue, the observed distribution is in black. This plot looks okay, but there's some obvious non-normality operating. This is why I report the bootstrapped results, because those are robust to non-normality. So the non-normality is not particularly problematic given that we have bootstrapping, but it is something we want to be cognizant about. If these lined up properly, instead of reporting the bootstrap, I might just report the original analyses. Okay, this plot is a QQ plot with a 95% envelope. It also addresses normality of the disturbance scores. It plots the residuals, or the disturbances, as a function of the quantiles of a normal distribution, which, if the disturbances are normally distributed, they should fall on a straight 45-degree angle upward on this line. I describe these plots in my book so you can get details about them there. We pay particular attention to data points that fall outside the 95% confidence band for the line. These guys up here. In this case, there's several of them, and that raises a red flag. Again, it's telling me to use the robust estimator because normality is an issue. Okay, this third plot addresses variance heterogeneity, and it plots the scores around each of the predicted values from the regression analysis. These are the predicted scores. And then here reflects the variability of the disturbances around the predicted scores. The variability should be about the same around the predicted scores. And that's roughly the case here. Now the variance heterogeneity is not going to be problematic, again because I'm using the bootstrapping. All right, let's take a look at this final plot. This is the smoothed plot that shows the mean predicted knowledge scores for each month based on the model, and those use the dashed line, and the observed or actual means of the knowledge scores for each month. These lines should be very close to one another. This is the Ebbinghaus curve here, and these are the actual mean scores at each of the predicted values. Now you can see there's pretty reasonable correspondence between these, and you don't have that bend back upwards that is unrealistic that the polynomial regression showed. Again, we have the Ebbinghaus curve that makes theoretical sense. But I've got some non-trivial disparity here at month 0, and it's a little bothersome to me that out here at the far end, I'm under-predicting knowledge by quite a bit. So this fit could be better. One possibility in modeling the data would be not to use nonlinear regression of the form that we're using, but rather to use spline regression. Now, I offer a program for spline regression on my web page. But when I look at this, I basically see two linear functions. There's a linear function here, and then there's a linear function here. And in spline regression, what you do is you take the curve and you split it into linear segments. In this case, I'd have a segment here with a line going here, and a segment here with a line going here. And then spline regression will give you the value of the slope or the regression coefficient within each segment, and it will do significance tests of the differences in the slopes between them. And I would bet that we could get a better fit using spline regression with the data. Another possibility would be just to add another constant to the Ebbinghaus model that would pull this back up and accommodate that disparity. But that gets tricky, and I don't want to get into that here. Yet another possibility would be to use dummy variable regression, where I regress knowledge onto the months, but I create 8 dummy variables to capture the means of every month in the model. That's rather inelegant, and I'd prefer to come at it by isolating a more parsimonious function if I can. Okay, there's another feature in the program that I want to show you. So let me close this out, go back to the program, and come back up to the input value box. The feature is the ability to conduct profile analyses, and that's what these boxes are used for. I can ask the program to do a more detailed analysis for different predictor profiles in the model. And this program gives you the ability to look at up to 4 distinct profiles. Now, if you have 9 profiles that you want to look at, for example, you can just specify 4 of the profiles in one run, then conduct another analysis where you use 4 other profiles. And you can iterate through multiple profiles by just doing additional runs. In this case, I'm going to ask the program to give me a more detailed analysis of the predicted knowledge scores when the value of month is 0. That is at the immediate recall period. And then here, I'm going to say also give me a profile analysis for the case where the delay in recall is 1 month. In here, I'm going to use 2 months. In here, I'm going to use 3 months. Now, it turns out the programming for this was kind of a nightmare. And I had to set it up so that if you ask for 1 profile, then you have to ask for 4 profiles. You can't just ask for 1 or 2. Now, if all you care about is 1 or 2 of the profiles, just put in other profiles that are bogus and that you don't care about. Okay, let me generate the output for these, and I'll walk you through it to explain what we're getting. And keep in mind that profile analysis is optional. You don't have to do it. I find it sometimes helps to interpret things. So I'm going to click on Register Input to generate the syntax. I'm going to copy that to the clipboard. I'm going to open up R. I'm going to press Control V. And here we go. Now the output starts up here, and it's exactly the same as before, so I don't need to review that with you. But then we get additional output surrounding each profile. And basically what I get for each profile is the predicted outcome score for that profile, or in this case, the predicted knowledge score. I get the estimated standard error for that, and I get the confidence intervals for the predicted value. So at the immediate recall, I'm predicting that the average knowledge score is 55, and it has a margin of error of about plus or minus 11. The lower limit here is about 11 units lower than this guy, and the upper limit of the CI is about 11 units above it. Now these confidence intervals are bootstrapped, so we don't have to make normality assumptions about them. And at month 1, I'm predicting that the mean knowledge score goes down to 37, give or take. Here's the standard error for it, and here are the bootstrapped 95% confidence intervals around that predicted mean score. So we can see that the knowledge scores go from around 55, according to the model, at month 0 down to 37 at month 1. And then if I go down, this does a difference between the first and second profile. And so the difference between 55 and 37 is about 17.9. And then this is the standard error of the difference and the confidence intervals around that difference. So the estimated decay of knowledge from immediate recall to 1 month after is about 17.9 units. And here are the confidence intervals around that. And then at month 2, here's the estimated knowledge score and the confidence intervals around it. And at month 3, here's the estimated knowledge score. And here's the difference between 3 and 4. So this last contrast here compares the decay that occurs between 1 and 2 with the decay that occurs between 3 and 4. It's the difference between those two differences. And this is the estimated difference between the differences, the standard error, and the confidence intervals. And by structuring your profiles in the input values box in strategic ways, you can flush out detailed information on different predictor profiles. And I find this to be very useful. Okay, you'll see examples of this in my book in the chapter on nonlinear modeling. And that's basically it for this video. Thanks a lot.